Today we have a tutorial on reactive synthesis, and in the lecture we already discussed what reactive systems are, and then we looked at what it means to do reactive synthesis. So just a quick reminder, a reactive system was a system that has an ongoing interaction with the environment by taking inputs from the environment and then producing outputs that have an effect on the environment. And the system has a specific goal, and these interactions, to simplify, we can just pretend they are infinitely long interactions, because there is not a specific thing where we say, well, after 10 steps the existence of this system ends. And then in reactive synthesis, what we said we do is we write specifications that are declarative and say what the system should do, and then we have a synthesizer that tries to figure out how the system can achieve the what that we ask it to do. And this can be either successful or unsuccessful, so synthesis can fail, and in our case, in the synthesis that we use, we know if synthesis fails, then there really is a problem with our specification. Then what we ask the system to do is not possible, given all the possible environments that the system could be in. But in case it is successful, in case the synthesis is successful, we know that the system will do exactly what we wrote in the specification. It will satisfy all the properties that we had in the specification. And one example of a reactive system is this robot here. Let me bring up the robot, and you can see that it has a sensor, and it also has actuators. It has these two motors. So what it does, it can sense the environment, and we also had in the last lecture, and we're going to have it here again, virtual sensors. So we can also have virtual sensors of how the robot can sense the environment. We had this emergency off button, and we had a work button where the robot was supposed to do some work or to shut down with the emergency off. And then we can also have virtual actuators. So these physical ones, it's clear what the motors do. They turn the wheels and the robot moves. And then we also had virtual actuators to extend this system a little bit. And it is a reactive system because the environment constantly changes when the robot moves and drives around. The readings that the sensor produces, or the readings that the virtual sensors get, whether it's emergency off or the robot needs to work, this is something that can constantly change, and the robot needs to react to it. So now let's see what our boss tells us today. So our boss tells us that the company sold a safety critical robot to customers, and now we need to program it because it has no software yet. But to avoid programming errors, we should synthesize the implementation. So we're not going to write the code ourselves, we're having the computer write the code for us. And we're going to use the same kind of setup here that makes it easy for us to re-synthesize code. So on the left side in this diagram, we see the robot with the ESP8266 chip, which is a really, really small computer that can't do much. It can just do some basic processing, and it is this one right here. And if you look on the back side, the main chip is actually only this silver box here. The rest is just some other components. So very small computer. It runs some C code. Now I made all the code available on GitHub. So on Blackboard you have a link to the GitHub page where you can get the code for the controller of the robot. And then we will have the robot connected to Wi-Fi. We will also have a server connected to Wi-Fi, which in this case will be my laptop. And on my laptop we're going to run a web server, very simple web server that is just for the communication with the robot. All the code of this is also available on GitHub, and this web server, it's really just maybe 10 lines of code, and then we have some wrapper that actually wraps the controller that we're going to synthesize. So we're going to use Spectra as we did in the computer labs for synthesis, and the controller that we're going to synthesize, it will be wrapped. There'll be a graphical user interface, which we had last time for the virtual sensors, basically, just 2 buttons, nothing more. And then this will be accessible through the HTTP server for the robot, and the robot will basically send some requests, and based on the synthesized controller, we're going to answer. What we had last week was we had here a code generated from a state machine, and then we had different versions of state machines that were where we generated the code from, and we could execute these on the robot by basically having the robot query what is the next step I should do, and then the generated code evaluates the sensors and says, okay, now the next step for you will be to go forward, and then that is what the robot would execute. And it basically every 50 milliseconds, if it's fast enough, every 50 milliseconds it will ask the server, okay, what should I do next? Are there any questions on this setup where we have the robot on one hand, on the one side, and the server on the other side that we're going to run on the computer? This is also now available on GitHub. It's linked from Blackboard. So there are 2 projects here. One is the project of the robot. There are some instructions. The robot code is really, really short. It is 155 lines of code, basically setting up the Wi-Fi and stuff like that, and controlling the motors. And there's a README here of what you need to do when you want to assemble it yourself. These are the kind of components that you could use to build it. Sometimes it's much cheaper to buy them in multiple packs. So here, if you buy a single motor controller, which is basically the motor controller is basically just this small thing here, and if you buy a single one, it's £5. If you buy 6 of them, it's £8. So browse a bit around if you want to build this robot or similar robots, because the prices might be quite different. So this is the software for the robot, and then we have the software for the computer that runs basically here on the server side. These are the plugins you might have to install. So here it says the official update site, but we used a little bit newer update site in the lab. So use the one from the lab instead. Soon we will also update this official update site, but yeah, use the one from the lab for now. This is how, yeah, and this is the code of the project. It's an Eclipse project, and here I have it running. So this is the project imported, and this is what we're going to use today. So we used it already last week for code generation from state machines. The state machines are here. This was the most complex state machine in the end that we built. And now let's see what happens when we try to write some specifications and run them on the robot. So the tasks of today are, first, it's a reactive system. So it is a little bit different from what we did with the state machine. If you remember, for the state machine, we were handling events. So we would basically check the sensor every 50 milliseconds, but then we would only call the event whether the robot is close to an obstacle. We would only call it if we are really close to the obstacle with less than 20 centimeters away, and only then we would call the actual event, and that would fire a transition, and then we would be in a state, and if the state is not listening to the too close event, then nothing would happen. So here in this robot, in this version, we also have the graphical representation. Maybe we should look at that. So here in this version, the state turning was listening for the clear event, but then the going is not listening for the clear event. So basically, in the state machine, we were just deciding what to listen to, and it was all events that happen at one point, and then we have actions that we execute at that point. This is how it worked in the state machines. Now, in the reactive synthesis, what happens is that we have some inputs that we're reading in every execution cycle, and then some outputs that we are setting in every execution cycle. So basically every 50 milliseconds, if the calculation is fast enough, roughly every 50 milliseconds, we will read the sensor and then say what next to do with the motors. So now it's basically the computation of the system is input output and not just event and action. So here we have the different inputs. One is the distance sensor, so we can call that distance, and it goes from 0 to 100 centimeters. We have a signal whether we are supposed to work or not. That's a Boolean. And then we have an emergency off switch, whether emergency stop is there or not. That's also Boolean. And then we have the commands for the motor, or the values that we can write to the motors. And these are now outputs, because this is what our controller will generate. And these are enumerations, so they can be forward, backward, or stop. And we have them twice, once for the left motor, once for the right motor. And then we also have this thing beep, which is our representation of, well, now the robot is working. So this work signal will be related to the beep. But right now, we're not going to use all of the inputs and outputs. We don't have to use all of them at all of the time. So for the first version of the robot, and this is very similar to what we did last time with state machines, is we're going to write a specification for the following behavior. The robot must not go forward when the measured distance is less or equal to 20 centimeters. So I already prepared a specification for that. Our robot here. I already put in a type definition for the motor command. And then we have the left and right motors, and initially we say the motors are stopping. So what should we do now to realize this requirement that the robot should stop or should not go forward when the measured distance is less or equal to 20 centimeters? Any ideas of how we would do that? So first, you can just put it in the chat if you have any ideas or any questions. You can also unmute yourself and ask. So the first thing we need is we need to define the input. We need to say that this is an environment controlled variable for the distance. And then, of course, it needs a data type. So here we said it's an integer that goes from 0 to 100, right? So this is now our input. Now we would be able to read, or this basically is the representation of what the robot would sense with the distance sensor here. Now we need to write some constraint, some temporal constraint, because it's not something that happens once. It's something that basically happens all the time. So at any point in time when the distance is less or equal to 20 centimeters, then the robot should not go forward, right? So any idea of how we would express this in a specification? So what we probably need is a guarantee, because this is something that we want the system to do. It's not something that we expect from the environment. It is something that we require from the system. So it's a guarantee. And then we say always, we can just say distance less or equal to 20. This would imply that we're not going forward. So now this forward actually doesn't exist, so we need to say what this forward is. We could write here directly that left motor equals forward, right motor equals forward, but this might be a lot to write. So what we could do is we could simply have a define, because we might need the forward later. So we want to define forward as left motor equals forward and right motor equals forward. Okay. Anything else that we need to do? Can we already synthesize a controller from this? Let's have a look. We can first maybe check realizability to check whether there are controllers that satisfy this, and it tells us it is realizable. Now, we might want to have a look at one of the controllers first. So let's say we want to synthesize a concrete controller. Oh, maybe there was a mistake. So we basically have many transitions because there are many possible sensor reading inputs that we could have. Should we just try to see what happens if we run it on the robot? So if we want to run it on the robot, what we don't want to take this thing is called a concrete controller, as you saw in the menu, and it is concrete because it lists basically the states and transitions for every step. But now let's say we want to run it on the robot, then what we want is a smaller representation which is not human readable but which the computer can read, and that is called a symbolic controller. So now we're going to synthesize the symbolic controller. And the symbolic controller is now written into this folder here. So now if we run our robot runner, what we can say is we have two engines here. One is the state machine engine, which we used last time, and the other one is the Spectra engine. So now we want to run using the Spectra engine, and it basically just selects a different kind of controller here. So let's try to run this. We have some output here initially when the synthesis, basically the interpreter for the symbolic controller, when it starts, it gives us some output. We can ignore that. Now we need to start the robot. And this is always a bit tricky. So we connect the power. Okay. The lights are on. Oh, something is happening. Okay, the robot is doing some it's doing something, right? It's using the mouse even. That gets dangerous. Okay. So it is behaving a bit chaotic. Now the question is, why does the robot behave in this chaotic way? Anybody got an idea? First, we might also want to check that it really does not go forward when the distance is. We have to start it again for that. Okay, so let's just make sure it really works according to the specification. So we see down here the output, right? Now I'm holding the robot. Now the distance is less than 20 centimeters. And we see that it doesn't go forward with both wheels at the same time. So it seems that it satisfies our specification. The only thing is that our specification is really underspecified, in the sense that we're not really telling the robot what to do. in all other cases. So we're just telling it, well, initially you should stop, then when the distance is less than 20 centimeters, you should not go forward. But it doesn't tell the robot anything else. It's basically completely up to the synthesizer to do something with the robot, but the synthesizer, of course, has no concept that the software that it's synthesizing is for some robot that is driving around. So it just kind of randomly does something that satisfies the specification. Okay, now let's check. In the preferences, we can set whether it's already, the settings are already fine. We can set whether the symbolic controller is deterministic, so which means that when it gets the same input at the same situation, should it always do the same? And yeah, that's better. So it's a bit more predictable. But we see that it's behaving quite randomly, but that's fine, because what our boss told us is that the robot must not go forward when the measured distance is less than 20 centimeters. Our boss didn't tell us anything else. So in theory, this would be fine. If we want to change that, we might want to require things that the robot maybe always eventually goes forward. So we want another guarantee that says always eventually the robot goes forward. So let's see, now it can still behave in very random ways, but we are restricting it a little bit more. Now let's see what happens when we check realizability. Anybody thinks that things will be fine? Or anybody sees a potential problem? It says it's unrealizable. Now, we learned in the lab that we can do stuff like calculating an unrealizable core. And then we see that these two guarantees together make the specification unrealizable. So what simply could happen is that the distance could always be less than 20 centimeters, and then there's no way we can go forward, right? So what should we do in this case? Anybody got ideas? We can simply drop this, and then it's we're not guaranteeing that it goes forward. But what we could do is we could also add maybe an assumption that there will be ways that the robot will get a distance that is larger than 20. So there are various ways to write assumptions. And here we could write some safety assumptions, but it's not really a safety thing that we can always, within a transition, guarantee that the distance will be larger than 20. And it's also not really something that always eventually happens, because if the robot stays in front of a wall, then always eventually the distance won't be smaller, won't be larger than 20 centimeters unless the wall falls down, right? So what we would want is we would want to relate in this assumption the distance to something that the system does. So basically, if the system does something to increase the distance, then the response to that should be that the distance is increased, right? And we know what the system can do to increase the distance. Well, if it simply turns, so let's define something like turn. If the left motor goes forward and the right motor goes backward, then the robot should be spinning in place. And then we can write something like a response pattern. For the patterns that we used also in the lab, we need to import the Dwyer patterns. The Dwyer patterns are this catalog of patterns right here. So it needs to be in the same folder or wherever we want to import it from. And then there is this response pattern here, this S response to P. And we could try to use that and say that S responds to P. So what is it that responds to what? If we are turning, then after some finite amount of time, the distance should be greater than 20, right? So we should be able to get to turn to somewhere where we have a larger distance again, and then hopefully it will be realizable so that we can then go forward again. So let's have a look, check realizability. It is now realizable. So let's see what happens when we synthesize a controller again. And now let's start the robot again. Okay, well, it's surely not getting stuck, and we also see that it's it still wants to use the mouse. I wonder what it would program if I put it on the keyboard. Okay, good. Yeah. So we would now have to find this always eventually forward thing. We can probably trust. Did we really? Let's check. Did this really get controller saved to disk? Okay. Yeah. Okay. So let's trust this that it goes always eventually forward because that's a guarantee. Now we can go to the next task where we should extend the specification to do this work again like we had last time. So when the work signal comes, the robot must stop both motors and beep. So there's an output beep. So if we want to write that, how would we write that? Any ideas? We first again need to put in the variables. So we have another environment variable of type Boolean, which is called work, and then we have a system variable of type Boolean, which is called beep. So this way the robot can know whether it has to work, and it can do the beeping by setting beep to true. Now, how do we make sure that it stops when there is a when work is turned on? We probably need some define for stop. Stop, we can do it like this. And then we should use that probably in some guarantee. So I'm just going to put the assumptions on top, and then the new guarantee that when there is work, we need to stop. This really sounds like a safety guarantee. So always work implies we need to stop, right? And then there was another one that said for working we also need to beep. So that's another guarantee that we can write. Always. So we could say work implies beep. The problem with this is that we would not restrict beeping from happening also when the robot is not working. But here, let's just say we want the robot to only beep if it has to work, if it is working. So we can do this if and only if. And now let's see what happens when we try to check realizability. Anybody got doubts that this is realizable? Okay, it's unrealizable. So, anybody sees why it's unrealizable? We can try to get a core calculated, Spectra, add-ons, cores, find an unrealizable core. and we see, oh, there is an issue with working and going forward. So what could happen is that the robot could be asked to work all the time, and then it would never go forward. So maybe we should do some exception here. So you always eventually have to go forward unless you're working, right? So if the robot is working, that's a good excuse to not going forward. So let's see if it's realizable now. It is, and let's synthesize another controller, and then let's run. Oh, we are still running. Okay, so then let's run it again. Okay, here we go. There's our graphical user interface with the work. We can set it to true. We can go back to false. Now let's start the robot. Oh, it's already driving. Yep, now, oh yeah. Okay, it now likes to go forward more than before, but yeah, that's fine. So now let's see if the work button works. So let's ask it to do some work. Okay, I don't know if you can hear the sound. I now hear this kind of chime. So it is working, and it's definitely stopping. Now let's say work is done. Oh, and then yeah, and then it decides to yeah, go again. Okay, so but driving backwards is a little bit dangerous here. So maybe we should change the specification so that it either, well, I mean, there are different ways to change the specification to avoid the driving backwards. So we could, for example, say always, never, never going back, right? So let's call this define backing, and then backward, but that's very restrictive, right? We're basically saying no matter what, don't go backwards. It's probably fine in this case because there is no need for the robot to ever go backwards, but I wonder if this is a good guarantee. Maybe what we should write is something like if the distance is greater than 20, then don't go backwards. Maybe that's a little bit better. Yeah, there is different syntax for implies, so I actually used this implies here. Okay, now yeah, should still be realizable. Yep, very good. And that is basically, I mean, to realize this, we just needed the two guarantees here. So the other one is just cosmetic stuff. So it's basically these two guarantees that we did for this extension right here, that when the robot is working, it must stop both motors and beep. Now, there is a further extension, and this further extension is whenever the emergency stop is pressed, then the robot must stop. So everybody who followed the implementation of the version 2, which now should be very capable of implementing this version 3, we need a new input, and then we need a new guarantee. Looks very simple. So let's try it. So now the input would be emergency stop. And then we would want the guarantee. This is, well, very, very similar to this one. I mean, we could even, if we wanted to, we could even extend this one we could say work or emergency off, then stop. So should we do this? Should we write work or emergency stop? Then we need to stop. Sounds good. Ooh, it's again unrealizable. Should we try to figure out why? So let's go to cores, find unrealizable core. And it is related, well, as we kind of suspected, to this. We either need to go forward or work, and then now there is another reason for stopping, that's the emergency stop. So what we could do is we could also say, well, if there's an emergency stop, that's also fine. Then you don't have to go forward. So if you're either working or there's an emergency stop, yeah, you're excused from going forward. Now it's realizable. And let's see if we can get a working system here. Oh, yeah, you don't see it, but the robot is still going. Okay, now let's try to shut it down. That took some time, but yes. So emergency off is pressed, and we see it here somewhere. No, we don't see it because this is just the output. So emergency off is pressed. Now, if we also do work at the same time, or at least I hear the ringing again. So now if we stop the work, the ringing should stop. It did. And now if we release the emergency off, the robot should move again. It has some issues with the distance. I mean, the distance measurements, they look a bit odd. Sometimes it detects 3 centimeters, 2 centimeters. So maybe there's something a little bit off with the sensor. Maybe maybe also some delays in the network, because now yeah. So I guess it's not really in these 50 milliseconds, but if the network is slowed down, then of course the messages, they will arrive at the robot a bit later. Okay, let's turn it off. Oh, no. Yeah, okay. So there is some slight delay. So maybe if you really want a better reaction time, you might want to put a maybe Raspberry Pi on this robot or something like that, another small computer, or just make sure you have a fast Wi-Fi. Okay, so yeah, now if we look back at this specification, what we see, these 6 lines here, they give us basically what is the input. This was a physical sensor, and these 2 are these visual sensors that we got in through the graphical user interface. Then we have 2 physical actuators, which are the motors right here, and this visual beep output that gives us a sound when the robot works. And this is basically what corresponds to this slide here, where we have the inputs and outputs. We just wrote them down into the specification. Then we have some definitions just to make writing these lines a little bit easier and make the lines a bit shorter overall. And then this one, we don't even need this. There was no requirement for that the robot initially stops. Then this one was basically implementing the first task. Then for the second task with the work, this is basically these 2 lines. And the third task was adding simply emergency stop to that line. These lines, we just added them for kind of cosmetics, because we don't want the robot to go too far backwards and drop off the table. So this was just to kind of fine-tune the synthesize behavior. And then here that we said always eventually forward, this was also something we just added because we we think it's probably a good idea to have that, but the specification here was not requiring it. So the total to implement these requirements in Spectra, this is really just these, how many lines? Yeah, if we want to make it realizable again, we probably have to take this line into account. So basically it's just those 4 lines of real constraints that we edit based on the requirements, and then we added 2 more lines because we think it's useful. I mean, we can be much more strict with this. We could simply say that here we could replace this one with a guarantee that says always distance greater than 20 implies forward. Now we don't even have this always eventually here, which means we could also even drop this assumption to make it much more simple. I'm not saying that this is necessarily better. Let's see what happens when we check realizability. It is unrealizable. Okay. Yeah, very good. So here we now have a, this is actually a very good sign for not writing these very specific guarantees. So here our very specific guarantee was when the distance is greater than 20, just go forward. But it is in conflict with reacting to emergency stops. So here we see that actually when there is an emergency stop, we need to stop. So, and when there's work as well. So we should probably update this, but this just gets more ugly. So we could say that not work or emergency stop and the distance is greater than that would together imply that we need to go forward. This might fix it. So yep, it is realizable. So now let's see what happens. If we synthesize a controller again, I hope we shut down everything. Yep. Now let's start the application again. I think the robot is still turned on. Yeah. Okay. Okay, now it has some issues with the distance sensor, but sorry, you can't see it. Let me bring it up. So now the robot just goes much more forward unless it hits the keyboard or something else, or there's an obstacle. Oh, okay. So this way we can, and of course the working feature still works, and the emergency stop feature also still works. Okay, this way we can fine-tune the behavior, but here you see we have to make these exclusions, and that's always a bit ugly to basically exclude cases where it should not go forward, and these are cases we can, usually a programmer might easily forget these exclusions. Sorry, I should stop the work. Yeah, okay. Now it stops ringing in my ears. Okay, so yeah, this is something that we had where we easily had written a conflicting requirement, and the good thing is that our synthesis environment allowed us to figure out what this requirement conflicts with. It told us, well, this conflicts with the stopping requirement from work and emergency stop. So the one way that you could use synthesis is basically you could put in a few requirements and then just check whether they are realizable together, because there are cases where you might have requirements which are conflicting, and then this synthesis approach, reactive synthesis approach, allows you to find out these conflicting requirements by calculating these unrealizable cores. Okay, Are there any questions? So now we managed to implement all these different versions. Are there any questions about the specifications or about the synthesis or the robot? If you have any questions, then just put them in the chat or unmute yourself.